So all the problems on the worksheet, we're going to be deciding which test to use between these 7. The 7 tests are divergence test, integral test, direct comparison test, limit comparison test, alternating series test, ratio test, and the root test. Number 1 asks you to determine if the integral converges or diverges for the series n squared over 1 plus n squared times e to the negative n. For this, the comparison test can be used. You know that n squared over 1 plus n squared is greater than 0 but less than 1 for all values of n, and e to the negative n is greater than 0 for all values of n. Using this, you can write the inequality, which is 0 is less than n squared over 1 plus n squared times e to the negative n, which is less than e to the negative n. And you know that e to the negative n converges due to geoseries, and r is less than 1 because r is 1 over e. And because the larger function has a finite integral and converges due to the geoseries, we can conclude using the comparison test that the original series also converges. Number 2 asks you to determine if the series converges or diverges. And the series is n to the third over n to the fourth plus 1 squared. To test for divergence, you can use the integral comparison test. So you have a sub n is equal to n cubed over n to the fourth plus 1 squared, and b sub n is equal to 1 over n to the fifth. So you want to find the limit as n goes to infinity of a sub n over b sub n. And so you plug in your values for a sub n and b sub n, and the limit as n goes to infinity is 1, which is greater than 0. So you know that 1 over n to the fifth converges by the p-test, where p is equal to 5, which is greater than 1. This can also be proved using the integral test. By the limit comparison test, we can conclude that the original series also converges. Number 3 asks to write a series for the given function and to determine if the series converges or diverges. And if the series converges, it asks you to find the sum. So to find what the series is equal to for the function, you want to see what the relationship between each term is. So you can see that from the first term to the second term, it is 2/3 the amount of the first term. So the first term times 2/3 would equal the second term. And so acknowledging this relationship, you can write that the series is equal to 2/3 to the power of n. Now, you also know that the series converges because it's a geometric series, and r, which is the ratio, is equal to 2/3, and the ratio is less than 1. Therefore, the sum from n equals 1 to infinity is equal to 17 over 63 over 1 minus 2/3. And this is a formula that you can memorize, which is the initial value over 1 minus the ratio. And this is equal to 17 over 21. Number 4 asks if the following series absolutely converges, conditionally converges, or diverges. And the series is 1 minus 1 over n raised to the n squared. And a little hint is given that the limit as n goes to infinity of 1 plus x to the n raised to the n is e to the x. And so it is important to know that you don't need to check for absolute convergence or conditional convergence because the function is always positive. It is not alternating. And in this case, you can use the root test. So you find the nth root of the given series, and you find the limit as n goes to infinity, and using the little hint they gave you, you can figure out that the limit as n goes to infinity is e to the negative 1. And this is less than 1. And therefore, the series is convergent by the root test. For number 5, the root test can also be used. So you find the nth root of the given series, which is n plus 3 raised to the 2n over 2n plus 7 raised to the 3n. And the limit as n goes to infinity is 0, which is less than 1. And therefore, the series converges using the root test. Number 6 asks if the following series converges or diverges, and the series is sine of n over n cubed. So for this, you can use the comparison test. The series is at most 1 over n raised to the 3 because the range of sine is -1 to 1. That's why 1 can be the largest value. And the series 1 over n to the third converges by p series, where p is equal to 3, which is greater than 1. Therefore, the original series also converges by direct comparison with p series. So for 7 and 8, you have to find how many terms are needed to guarantee 4 decimal places of accuracy when you find the sum. So for number 7, it is a non-alternating series, so the remainder test can be used, and you must round up for the number of terms that you need. And so you find the integral of the series, and then you set that equal to how many decimal places of accuracy you want. In this case, it is 0.00005 because you want 4 decimal places of accuracy. And you can solve for n, and in this case, you get 8.4. And because it's a non-alternating series, you want to round up, and so the number of terms needed would be 9 terms. A helpful tip when you're trying to find the value of n is to graph the integral and how many decimal places of accuracy you want. And then on your graph, you can find the point of intersection, and that's going to be your value for n. The main difference between 7 and 8 is that 8 is an alternating series. So for alternating series, you set the integral equal to the error, and you round down because the next term would be the error. And so you would take your series and set it equal to 0.0005 because that's your error, and you solve for n, and you get 9.2. And in this case, you would round down, so n would equal 9 terms. And that's just the number of terms you need to guarantee 4 decimal places of accuracy. Number 9 asks if the following series converges or diverges, and the series is n plus 6 over n plus 1. So first thing to notice is that the integral is positive and it is decreasing. And so we can use the integral test. The limit as t goes to infinity of the integral of x plus 2 over x plus 1 is equal to infinity. And therefore the series diverges using the integral test. So the neat thing about number 10 is that it is an alternating series. And so when you have an alternating series, it is always helpful to write out the first couple of terms so you can recognize the pattern and see what sort of cancellation happens. And so the first couple of terms of this series are cosine 1 minus cosine 1/4, and then the next term would be cosine 1/4 minus cosine 1 over 9. And from this you can see that the cosine 1/4 and the cosine 1/4 here will cancel out because one's negative and one's positive. And so you can write a general rule for the series as well, which would be cosine 1 over n squared minus cosine 1 over n plus 1 squared. And this would equal to the limit as n goes to infinity would equal to cosine 1 minus cosine 0 because these middle terms would cancel out and you would be left with the first term and limit as n goes to infinity of the last term. And so you would end up with cosine 1 minus 1, and therefore you know that the series converges. We're going to look at 2 different ways to do number 11. Now, number 11 asks for if the sequence converges or diverges, and the sequence is -1 raised to the n times 2n squared plus 3 over n squared plus n plus 1. So one way to look at it is to find the limit as n goes to infinity of a sub n, and this is when the value of n would be even. So when the value of n is even, the sequence is positive. So the limit as n goes to infinity would be 2. However, for odd values of n, the limit as n goes to infinity would be -2. And therefore the series diverges. Another way to look at number 11 is to use the alternating series test. So the 2 criteria needed for the alternating series test is 1, the sequence must be decreasing, and 2, the limit as n goes to infinity for the sequence must be 0. So to see if the sequence is increasing or decreasing, you can find derivative of the sequence, which would, in this case, be low d high minus high d low over low squared. And for large values of n, the derivative would be negative, and so therefore the sequence is decreasing. However, the limit as n goes to infinity of a sub n, which is your sequence, is 2 and not 0. So the sequence diverges by the alternating series test. Number 12 asks you to determine if the series is absolutely convergent, conditionally convergent, or divergent. The series given is negative 1 raised to the n times n squared over 4 to the n. In this case, the series is alternating, and so it is possible that you have a case that is conditionally convergent or just divergent or absolutely convergent. And so for this, you can use the ratio test. When you use the ratio test, you'll find the limit as n goes to infinity of n plus 1 over n raised to the second power times 4 to the n over 4 to the n plus 1. And the limit as n goes to infinity is 1/4, and 1/4 is less than 1, and so therefore the series converges absolutely. So you don't need a test for conditional convergence. It is important to remember to state what test you use. When using p-series or geoseries within a problem, it is important to state the value of p and r because p must be greater than 1 and r must be less than 1. Another common mistake is assuming that one series diverges or converges without making sure that the one that converges is greater and the one that diverges is smaller.